The wind cut different at 8,000 feet in the Wind River Valley. James McGregor learned that his first winter in 1824, when ice formed on the inside walls of his shelter and his water bucket froze solid just 3 feet from his fire. He had built his camp exactly the way every trapper in the Rocky Mountains was told to build it: enclosed tent with thick hides, fire burning inside, standard and proven by company manuals. By late winter, he had burned through more firewood than two men should need, and still the cold crept through every gap. Across the high country, trappers and mountain men were fighting the same losing battle in shelters built by the book and failing by the season. Over the next 2 winters, McGregor quietly adapted techniques from older traditions to create a shelter system that stayed warmer, used less wood, and kept him alive through blizzards that drove others down the mountain. Today I'll break down the exact setup, the measurable differences, and the forgotten principles behind his results. What did McGregor understand about heat and shelter that every serious outdoorsman today should know, but almost no one does? The morning after that first brutal night, McGregor walked through the scattered camps along Beaver Creek and saw the toll. Thomas Bridges, the company foreman, stood outside his regulation tent shaking ice from a frozen buffalo robe, cursing the wind that had torn loose 2 corner stakes despite careful anchoring. The tent fabric, though doubled with elk hide, had collected frost on the interior surface thick enough to scrape with a knife blade. Bridges had kept his fire burning through most of the night, feeding it split pine every 2 hours, yet the far corners of his shelter had dropped cold enough to freeze the water, and his tin cup solid. 3 camps down the creek, a newer trapper named Samuel Cross had attempted the quick log cabin approach, cutting and notching pine logs into a tight rectangle with a stone fireplace built into the gable end. Cross had followed the standard frontier manual precisely: logs chinked with mud and moss, door facing away from prevailing wind, fireplace drawing properly up the stone chimney. But the cabin's single room had proven too large for the heat generated, and the stone chimney drew so much warm air upward that Cross spent the night huddled within arm's reach of the hearth, his back freezing while his face burned from direct flame exposure. McGregor had seen such failures before during his 7 years working the Ohio frontier, but the high altitude and persistent wind of the Rocky Mountains amplified every flaw in conventional shelter design. The Scottish-Irish immigrant had learned basic timber framing from Swedish carpenters in the Great Lakes logging camps, and later spent 2 seasons working alongside a French-Canadian brigade that moved through Shoshone territory. During that time, he had observed something that stayed with him: the winter. Camps of the new people positioned their fires differently than any white trapper he had known. The Shoshone elder, who traded occasionally with their brigade, had built his winter shelter as a low framework of willow poles covered with buffalo hides, but instead of fully enclosing the space, he left the front face open toward a fire placed 4 paces away. McGregor had watched the old man sleep comfortably through nights that drove the French Canadians deep into their enclosed tents, and when he asked about the arrangement, the elder had gestured toward the fire and shelter together, speaking broken English about sleeping with the fire, not inside it. Most of the trappers in McGregor's current brigade dismissed such observations as primitive foolishness. Bridges particularly scoffed at what he called half-shelter nonsense, arguing that proper frontier wisdom meant full enclosure against the elements. "We've got canvas and timber," Bridges would say, "not some hide contraption with gaps for the wind." The other men agreed, pointing to military manuals and trading company guides that consistently recommended tight construction and internal heating as the proven method for mountain survival. But McGregor had noticed something during his winter with the Shoshone camps that contradicted the standard approach. The indigenous shelters, despite their open fronts, maintained more consistent warmth throughout the sleeping area than the fully enclosed tents used by the white trappers. The fire positioned outside the shelter opening seemed to create a field of radiant heat that penetrated the entire space, while the fires built inside enclosed shelters lost much of their heat to the walls and roof, creating hot spots near the flame and cold zones in the corners. The principle emerging in McGregor's mind challenged the fundamental assumption behind frontier shelter design. Every trapper manual and company guide treated the shelter and fire as separate components. Build a weatherproof enclosure, then heat the interior with a contained fire. But McGregor began to suspect that effective winter survival required treating the fire and shelter as a single integrated system, with the positioning and interaction between the two elements determining the overall performance. This insight had been reinforced during his time learning carpentry from Anders Olsen, a Norwegian immigrant who had adapted Old World building techniques to American frontier conditions. Olsen had shown McGregor how European loggers built low, lean-to shelters that faced their fires directly, creating what he called heat reflection between the flames and the angled shelter wall. Olsen's shelters used less fuel and maintained more even temperatures than the enclosed cabins preferred by most American builders. But the technique had never gained acceptance among mountain men who trusted only fully weatherproofed construction. Now, watching his fellow trappers struggle through their second week of brutal cold despite following all the accepted methods, McGregor decided to test the principle that had been forming in his mind since his time with both the Shoshone elder and the Norwegian carpenter. The conventional wisdom held that survival meant building the strongest possible barrier between yourself and the weather, then generating enough heat inside that barrier to overcome the cold. But McGregor suspected that the key lay not in blocking the environment, but in positioning himself and his fire to work with the natural behavior of radiant heat. He began planning a shelter system that would place him between the fire and a reflective surface, rather than surrounding him with walls that absorbed and dissipated heat. The idea seemed counterintuitive to men trained in the frontier belief that more enclosure meant more protection, but McGregor had observed its success in two different traditional systems that had developed independently of American trapper methods. As January deepened and the failures of conventional camps multiplied around him, McGregor committed to building and testing what he privately called the fire shelter system. He would construct a half shelter oriented toward an external fire, position his bedding between the heat source and a reflective back wall, and measure the results against the enclosed tents and cabins that surrounded him. If the principle proved sound, it would overturn decades of accepted frontier wisdom. If it failed, the cost would likely be his life in the unforgiving cold of the Wind River winter. The test would determine whether survival in extreme conditions required following the established methods that everyone trusted, or understanding the fundamental principles that made those methods work or fail. McGregor chose his test site with the precision of a military engineer surveying a battlefield position. The spot lay 50 yards upstream from the main brigade camp, on a slight rise that elevated the location 3 feet above the creek bottom where cold air settled at night. The ground sloped gently southward, providing natural drainage for snowmelt, while offering protection from the north winds that funneled down the valley with devastating force after midnight. Most importantly, a cluster of granite boulders on the north side created a windbreak without blocking the morning sun that would strike the site from the southeast. This site selection contradicted standard trapper practice, which prioritized flat ground near water sources for ease of construction and convenience. McGregor understood that flat creek bottom locations collected the coldest air through a process meteorologists would later call thermal inversion, where dense frigid air sank into low-lying areas like invisible rivers of cold. By positioning his shelter on the rise, he placed himself above this cold air drainage while still maintaining access to water and timber. The shelter framework itself measured exactly 6 feet wide by 8 feet deep, with the highest point reaching 5½ feet above ground level. McGregor cut 12 lodgepole pine saplings, each 3 inches in diameter, and lashed them into a lean-to frame using rawhide strips that would tighten as they dried. The frame sloped at a 30-degree angle from the high front edge to the low back wall, creating an interior space just large enough for one man to sleep comfortably while minimizing the volume of air that needed heating. The covering consisted of 2 buffalo hides sewn together and stretched over the frame, with the hair side facing inward to trap air and the smooth side facing outward to shed precipitation. McGregor left the entire front face of the shelter completely open, creating a rectangular opening 6 feet wide by 4 feet high that would serve as the entry point for radiant heat from his fire. The fire location required mathematical precision that McGregor had learned from watching the Shoshone elders' camp geometry. He positioned the fire pit exactly 4½ feet from the shelter opening, measured by pacing off the distance heel to toe 6 times. This distance proved critical, closer than 4 feet, and the direct flame created uncomfortable hot spots, while smoke occasionally drifted into the shelter. Farther than 6 feet, and the radiant heat dispersed too widely to effectively warm the sleeping area. McGregor dug the fire pit 18 inches in diameter and 6 inches deep, lining the bottom with flat stones to retain heat and prevent the fire from burning down into the frozen earth. Around the pit, he arranged a circle of larger rocks that would absorb heat during active burning and continue radiating warmth for hours after the flames died down. These thermal mass stones, each weighing 15 to 20 pounds, essentially functioned as a primitive radiant heating system that extended the effective burning time of each load of fuel. Behind the shelter, McGregor constructed what he termed his heat wall, a reflective barrier designed to capture and redirect radiant energy back toward his sleeping position. Using the granite boulders as a foundation, he built a curved wall 3 feet high and 8 feet long, filling gaps between stones with smaller rocks and clay mud. The wall's curved shape focused, reflected heat toward the center of the shelter opening like a primitive parabolic mirror, concentrating the thermal energy instead of allowing it to disperse randomly into the night air. The first test came during a clear January night when the ambient temperature dropped to minus 15 degrees Fahrenheit. McGregor built his fire using seasoned pine split into pieces 18 inches long and 3 inches thick, creating a sustainable burn that would maintain consistent heat output over extended periods. He began with a hot fire to warm the thermal mass stones, then banked the coals using a technique the Shoshone elder had demonstrated, arranging larger pieces over a bed of glowing embers to create steady, radiant heat rather than flickering flames. At sunset, McGregor measured the temperature inside his shelter opening using a mercury thermometer he had acquired from a surveyor in St. Louis. The reading showed 22 degrees Fahrenheit, while the ambient air temperature registered minus 8 degrees, a 30-degree differential created entirely by radiant heat reflection and wind protection. As the night progressed and outside temperatures continued falling, the differential actually increased rather than decreased, reaching 35 degrees by midnight. Meanwhile, Thomas Bridges, in his regulation tent 300 yards downstream, recorded interior temperatures that barely stayed above ambient levels, despite maintaining a fire inside his enclosed space. Bridges burned through 65 pounds of split pine during the night shift, constantly feeding his fire to combat heat loss through the tent walls and roof ventilation. McGregor achieved superior warmth using only 42 pounds of wood, a 35% reduction in fuel consumption, while maintaining higher interior temperatures throughout the night. The key breakthrough came from understanding heat transfer principles that conventional shelter design ignored completely. Enclosed tents and cabins trapped heated air, but that air immediately began losing energy through conduction to cold walls, convection through fabric gaps, and radiation upward through roof openings. McGregor's open front design eliminated these heat loss mechanisms by positioning the occupant directly in the path of radiant energy from the fire, while the reflective wall behind him bounced additional heat back toward his body. This radiant heating approach proved far more efficient than the convective heating used in enclosed shelters. Instead of warming air that would immediately escape, McGregor's system warmed objects, the stones, the reflective wall, his own body, and the ground beneath him, that continued radiating stored heat long after the fire burned down to coals. The thermal mass effect meant that even when he allowed the fire to die back during deep sleep periods, the accumulated heat in the stone surfaces maintained comfortable conditions until morning. By dawn, McGregor had documented a revolutionary discovery that challenged 2 centuries of frontier shelter theory. The standard approach of maximum enclosure with internal heating actually worked against the fundamental physics of heat transfer in sub-zero conditions. His fire shelter system demonstrated that strategic positioning and heat reflection could achieve superior results with significantly less fuel and labor, providing a sustainable method for extended winter survival that conventional techniques could not match. McGregor's first week in the new shelter revealed a critical flaw that threatened to undermine his entire system. Despite achieving remarkable air temperatures within the fire-warmed zone, he woke each morning with deep cold penetrating his body from below, as if the frozen earth itself was drawing away his vital heat through direct contact. The problem became acute during a 3-day stretch when ambient temperatures never rose above minus 20 degrees Fahrenheit, and McGregor found himself losing body heat to the ground faster than his fire system could replace it. The issue lay in conductive heat transfer, a principle McGregor understood instinctively from his carpentry background but had failed to account for in his shelter design. While his fire reflection system successfully warmed the air around his sleeping position, the frozen ground beneath him acted like a massive heat sink, conducting thermal energy directly from his body into the Earth's frozen mass. This ground contact represented the largest single source of heat loss in his system, potentially fatal during extended exposure to sub-zero conditions. McGregor's solution drew from techniques Anders Olsen had demonstrated during their logging camp partnership in Minnesota. Olsen had built raised sleeping platforms in the timber crew's lean-to shelters, elevating the men's bedding 8 to 12 inches above ground level to break the conductive connection between body heat and frozen earth. McGregor adapted this principle by constructing a sleeping platform from split lodgepole pine logs, each piece measuring 4 inches in diameter and 6 feet in length. The platform construction required precise engineering to support a man's weight while maintaining structural integrity through repeated freeze-thaw cycles. McGregor laid the foundation logs parallel to each other, spacing them exactly 12 inches apart center to center, then lashed a second layer perpendicular to the first using rawhide bindings. This created a grid framework that distributed weight evenly while allowing air circulation beneath the sleeping surface. The finished platform stood 10 inches above ground level, creating an insulating air gap that virtually eliminated ground conduction. Over this wooden framework, McGregor layered a sophisticated insulation system that combined techniques from both his Norwegian carpentry mentor and the Shoshone winter camps he had observed. The bottom layer consisted of dried grass gathered from meadows during the previous autumn, bundled into thick mats and laid 12 inches deep across the entire platform surface. This grass layer trapped air in thousands of tiny pockets, creating what modern scientists would recognize as cellular insulation with exceptional thermal resistance. Above the grass, McGregor spread his primary buffalo robe with the hair side facing upward toward his body. The buffalo hide measured 7 feet by 5 feet and weighed nearly 30 pounds when dry, providing both insulation value and wind protection around the edges of his sleeping area. The dense underhair of the buffalo created thousands of air-trapping cells, while the longer guard hairs shed moisture and provided additional thermal barrier. His blanket system represented a radical departure from standard trapper bedding practices. While most mountain men used a single heavy blanket or robe and attempted to strip down to underclothing for sleep, McGregor maintained full winter clothing throughout the night and added layers rather than removing them. He wore wool pants, a flannel shirt, a leather vest, and heavy wool socks, creating multiple insulation layers against his skin that trapped warm air between fabric surfaces. Over his clothed body, McGregor pulled a deer hide blanket that he had prepared using brain tanning methods learned from Shoshone women during his earlier brigade seasons. This deer hide measured 6 feet by 4 feet and provided a lighter but highly effective outer layer that sealed body heat while allowing moisture vapor to escape gradually. The brain-tanned leather remained flexible even in sub-zero temperatures, unlike commercially prepared hides that became stiff and cracked in extreme cold. The layering sequence proved crucial for thermal efficiency. McGregor's body heat warmed the air trapped between his clothing layers, while the deer hide blanket prevented that warm air from escaping. The buffalo robe beneath him provided insulation from below, while the raised platform eliminated ground conduction entirely. This created what thermal engineers would later term a thermal envelope, a controlled microenvironment where body heat could accumulate and circulate without significant loss. During mid-January, McGregor tested his insulation system during a severe cold snap that brought ambient temperatures down to minus 28 degrees Fahrenheit. Using the same mercury thermometer that had measured his fire system performance, he recorded temperatures within his bedding layers that stayed consistently between 15 and 20 degrees Fahrenheit, a remarkable 45 to 48 degree differential above ambient conditions. His body core temperature, measured by holding the thermometer against his chest for 3 minutes each morning, remained in the normal range throughout the test period. The insulation system also demonstrated remarkable efficiency in terms of body heat retention over time. McGregor discovered that once his layered bedding reached optimal temperature, usually within 30 minutes of lying down, it maintained thermal stability for 8 to 10 hours even when his fire burned down to minimal coals. His body heat, combined with residual warmth from the fire system, created a sustainable thermal cycle that required no additional fuel input during sleep periods. Meanwhile, other trappers in the brigade continued struggling with ground-based heat loss despite their enclosed shelters. Samuel Cross, sleeping on the dirt floor of his log cabin, recorded ground temperatures of -15 degrees Fahrenheit directly beneath his bedding, creating continuous conductive cooling that his internal fire could not overcome. Thomas Bridges, sleeping on canvas in his regulation tent, experienced similar ground losses that forced him to maintain active fires throughout the night just to prevent hypothermia. McGregor's platform and layering system revealed another critical principle that conventional frontier wisdom had overlooked entirely. Effective winter survival required controlling heat loss from all surfaces of the human body simultaneously, top, bottom, and sides, rather than simply generating more heat from a single source. His integrated approach to insulation created thermal protection that worked synergistically with his fire reflection system, producing results that neither component could achieve independently. By late January, McGregor had perfected an insulation methodology that virtually eliminated the two primary causes of hypothermia in winter camping: ground conduction and convective cooling. His raised platform, grass underlayment, buffalo robe base, and deer hide covering created a thermal envelope that sustained comfortable sleeping conditions using only his body heat and residual fire warmth, proving that proper insulation design could be more effective than increased fuel consumption for extended cold weather survival. McGregor's fire management breakthrough came during a brutal February night when his initial approach nearly cost him everything. He had been maintaining his fire using standard trapper methods, building a hot flame with quick-burning kindling, then feeding larger pieces throughout the night to sustain heat output. But this conventional approach created a dangerous cycle of temperature fluctuations that left him vulnerable during the deepest cold hours between midnight and dawn. The crisis occurred during his third week of testing, when McGregor woke at 2 a.m. to find his fire reduced to a small pile of glowing embers, and his shelter temperature dropping rapidly toward dangerous levels. Outside, the wind had picked up to steady gusts that scattered his remaining coals and made relighting difficult in the darkness. As he struggled to rebuild the fire using frozen kindling, his core body temperature began dropping despite his insulation system, and he realized that sporadic fire management could prove fatal regardless of his shelter and bedding innovations. The solution emerged from careful observation of fire behavior patterns that most trappers ignored completely. McGregor discovered that different wood sizes and burning sequences created vastly different heat output curves over time. Quick-burning materials like pine kindling produced intense but short-lived heat, while larger pieces burned cooler but maintained temperature for extended periods. The key lay in orchestrating these different burn rates to create sustained radiant output, rather than the peaks and valleys of conventional fire feeding. McGregor developed what he termed his banking system, a methodical approach to fire construction that prioritized steady heat output over dramatic flames. Beginning at sunset, he built his fire using a 3-stage fuel progression that would maintain optimal burning throughout the night. The foundation layer consisted of hardwood pieces cut to 24 inches in length and split to 4-inch thickness, arranged in a tight parallel formation that created maximum surface contact between pieces. Over this base layer, McGregor placed a second tier of slightly smaller pieces, 20 inches long and 3 inches thick, positioned perpendicular to the foundation logs to promote airflow while maintaining fuel density. The top layer consisted of split pine pieces 18 inches long and 2 inches thick, which would ignite quickly to establish initial heat, while the hardwood foundation slowly caught fire and began producing the steady coal bed that would sustain overnight burning. This fuel architecture produced a controlled burn sequence that eliminated the temperature fluctuations plaguing conventional fire management. The pine ignited immediately, creating rapid heat buildup and strong draft that pulled the hardwood pieces into active combustion. As the pine burned down over the first 2 hours, the hardwood maintained increasingly steady heat output, eventually forming a bed of glowing coals that radiated consistent thermal energy for 8 to 10 hours without additional feeding. MacGregor's fuel preparation regimen demonstrated remarkable efficiency compared to the haphazard wood gathering practiced by most trappers. Each afternoon, he spent exactly 2 hours cutting and splitting his overnight fuel supply, producing 45 to 50 pounds of wood size specifically for his banking system. He cut all pieces using precise measurements, 24 inches, 20 inches, and 18 inches, ensuring optimal burn progression regardless of wood species or moisture content. The splitting technique MacGregor employed created fuel pieces with maximum surface area exposure, accelerating ignition while maintaining structural integrity for sustained burning. He split each log along the grain into pieces with consistent thickness, avoiding the irregular chunks that burned unpredictably and wasted thermal energy. This systematic approach to fuel preparation required more initial labor, but eliminated the need for middle-of-the-night fire maintenance that exhausted other trappers and compromised their sleep cycles. MacGregor's most revolutionary innovation involved integrating his sleep schedule with fire management cycles, rather than fighting against natural burning patterns. Instead of attempting to maintain continuous wakefulness to feed his fire, he developed a two-phase sleep system that worked with his banking method to provide optimal rest while ensuring thermal safety throughout the night. The first sleep phase lasted from approximately 9 in the evening until 1 in the morning, during which MacGregor slept deeply while his banked fire progressed through its initial burning stages. At 1 o'clock, he woke briefly to assess coal development and add 3 carefully sized pieces, 20 inches long and split to 3-inch thickness, that would sustain the coal bed through the second sleep phase. This middle-of-the-night feeding required less than 10 minutes and minimal movement outside his insulated bedding system. The second sleep phase continued from 1:15 until dawn, sustained by the renewed coal bed that provided steady, radiant heat without requiring additional attention. MacGregor discovered that this interrupted sleep pattern, rather than producing fatigue, actually improved his overall rest quality by synchronizing his sleep cycles with optimal fire performance. The brief midnight awakening prevented the deep hypothermic stress that occurred when fires died completely, while the 2 sustained sleep periods provided adequate rest for the next day's activities. This sleep-fire integration required MacGregor to prepare his midnight fuel addition during daylight hours, prepositioning 3 precisely sized pieces within arm's reach of his sleeping platform. He also developed a rapid fire assessment technique that allowed him to evaluate coal development and make feeding decisions within minutes of waking, minimizing heat loss from his bedding system during the brief maintenance period. The efficiency gains from MacGregor's systematic approach proved dramatic when compared to conventional fire management. Thomas Bridges, maintaining his tent fire through continuous feeding, consumed 70 to 80 pounds of wood per night while experiencing significant temperature fluctuations that disrupted sleep and increased hypothermia risk. MacGregor achieved superior thermal stability using 45 to 50 pounds of wood, a reduction of 30 to 40%, while obtaining better rest through his planned sleep phases. MacGregor's banking system also eliminated the dangerous emergency situations that plagued other trappers when fires died unexpectedly during deep sleep. His coal bed approach ensured that even if he overslept past his planned midnight feeding, sufficient embers remained active to restart full burning with minimal effort. This thermal safety margin proved crucial during severe weather periods when emergency fire building could mean the difference between survival and death. By late February, MacGregor had perfected a fire management methodology that transformed overnight heating from a constant struggle into a predictable system. His banking techniques, systematic fuel preparation, and sleep cycle integration created sustainable fire performance that supported his shelter and insulation systems while requiring less labor and fuel than conventional approaches. The combination demonstrated that effective winter survival depended not on working harder to generate heat, but on understanding and controlling the fundamental processes that determined how heat was produced, sustained, and utilized throughout the critical overnight period. The storm that would test MacGregor's system beyond all previous limits arrived on the morning of February 23, 1825, with a ferocity that veteran trappers would remember for decades. By noon, snow was falling so heavily that visibility dropped to less than 10 feet, and the wind had built to sustained gusts that bent lodgepole pines horizontal and created snowdrifts 8 feet deep within hours. Weather conditions that had challenged McGregor's fire shelter insulation system during clear nights now combined into a prolonged assault that would either vindicate his methods or expose fatal flaws that conventional wisdom had correctly avoided. McGregor's first adaptation involved structural modifications to his shelter frame that he implemented as the storm intensified throughout the afternoon. The sustained wind pressure and accumulating snow load threatened to collapse his lean-to framework, which had been designed for normal winter conditions rather than the extreme forces now battering the valley. Using techniques learned from his timber framing background, McGregor added diagonal bracing members between his vertical support posts, creating triangular reinforcement that distributed wind loads across the entire frame structure instead of concentrating stress on individual joints. He also modified his shelter covering system to prevent wind-driven snow penetration while maintaining the open front that his heating system required. McGregor repositioned his buffalo hide covering to create overlapping flaps at the shelter opening, forming a baffle system that blocked horizontal snow while allowing radiant heat from his fire to enter the sleeping area. This wind-snow barrier represented a critical innovation that preserved his fire reflection heating while protecting against the penetrating moisture that destroyed insulation. Effectiveness in other shelters. The blizzard's most severe challenge came from fuel supply logistics, under conditions that made normal wood gathering impossible. McGregor had prepared for extended storms by stockpiling a 3-day fuel reserve, but the current weather system showed signs of lasting far longer than his standard preparation anticipated. Working during brief lulls in the wind, McGregor implemented an emergency fuel conservation strategy that extended his supply while maintaining adequate heat output for survival. This conservation approach involved modifying his banking system to achieve maximum thermal efficiency from minimal fuel input. Instead of his standard 50-pound overnight fuel load, McGregor reduced consumption to 35 pounds by using smaller pieces that created more complete combustion and higher heat output per pound of wood burned. He also employed a technique observed during Shoshone winter camps, building a reflector screen from flat stones positioned behind his fire to redirect radiant energy that would otherwise disperse into the storm, effectively doubling the heating value of each piece of fuel. McGregor's emergency protocol included rationing his fuel supply into daily allotments while maintaining detailed consumption records using charcoal marks on a pine board. This systematic approach to resource management under crisis conditions demonstrated planning principles that separated successful mountain men from those who died during unexpected weather events. By the second day of the storm, McGregor had documented fuel consumption rates that would sustain his heating system for 6 days, rather than the 3 days his original stockpile had been designed to provide. Meanwhile, the conventional shelter systems used by other brigade members began failing catastrophically under storm conditions they had never been designed to withstand. Thomas Bridges watched his regulation tent collapse when accumulating snow overloaded the canvas roof, forcing him to abandon his shelter and seek refuge in Samuel Cross's log cabin. Cross's structure, though more substantial than a tent, suffered chimney blockage when wind-driven snow clogged the stone flue, filling the interior with smoke and forcing the occupants to extinguish their fire to prevent asphyxiation. The cascade of failures among standard shelters revealed fundamental design weaknesses that normal winter conditions had masked. Enclosed structures that trapped heated air also trapped moisture from breathing and cooking, creating interior condensation that froze on walls and ceilings, reducing insulation effectiveness, and creating hazardous ice formations. Cross documented interior ice accumulation reaching 2 inches thickness on his cabin's north wall, while water condensation from 4 men's breathing created puddles that froze solid on the floor, making movement dangerous and eliminating any possibility of ground-level warmth. McGregor's open front design eliminated these moisture problems completely, while his fire reflection system continued providing steady heat throughout the storm's worst periods. His temperature measurements, recorded every 6 hours using the mercury thermometer, showed remarkable stability even as conditions outside deteriorated beyond anything he had previously experienced. When ambient temperatures reached minus 32 degrees Fahrenheit during the storm's peak intensity, McGregor's sleeping area maintained a consistent 12 degrees Fahrenheit, a 44-degree differential that sustained comfortable survival conditions while other shelters became uninhabitable. The storm's duration ultimately lasted 60 hours, during which McGregor consumed 120 pounds of fuel compared to the emergency sharing of fuel resources among the 4 men crowded into Cross's compromised cabin, who burned through more than 300 pounds of wood while achieving inferior heating results and risking carbon monoxide poisoning from their blocked chimney system. McGregor's systematic approach to fuel management and structural adaptation had achieved nearly 3-to-1 efficiency advantage while maintaining superior safety and comfort throughout the crisis. On the morning after the storm cleared, McGregor emerged from his shelter to find that his integrated system had performed exactly as designed under the most severe conditions the Rocky Mountain winter could produce. His shelter frame showed no structural damage. His fuel supply remained adequate for continued operation, and his physical condition remained strong enough for normal trapping activities. In contrast, the conventional shelter users required 2 days of recovery before resuming work, while Cross's cabin needed major repairs to restore habitability. The demonstration convinced William Harper, the fur company outfitter responsible for evaluating winter survival methods, to document McGregor's techniques in his official reports to company headquarters in St. Louis. Harper's measurements and observations would eventually influence company recommendations for trapper training and equipment procurement, introducing McGregor's fire reflection and systematic fuel management principles into official frontier survival protocols. The validation of McGregor's methods during the February blizzard marked the transition from experimental techniques to proven survival systems that could be taught, replicated, and relied upon under the most challenging conditions. His integration of site selection, fire placement, insulation design, and fuel management had created a winter survival methodology that outperformed conventional approaches by measurable margins while requiring less labor and resources. The storm had provided the ultimate test that proved superior understanding of thermal dynamics, and systematic preparation could overcome extreme environmental conditions that defeated traditional methods based on conventional wisdom alone.